So I've been doing this little speech for so long, I forgot who I've done it. We haven't done anything for the review yet. Is that correct? I haven't mentioned really anything about the test or the final exam. Okay, so let's give you the big picture, and then we'll get into hopefully some specifics. Oh, first question. Any volunteers? What day is our final exam?
Wednesday at 7.
So you're correct. It's on Wednesday, the 15th of June. It's going to last you 3 hours. And it's going to be 7 till 10 a.m. You will then get 30 minutes after that. So by 10:30, you have to have all your working uploaded and put into Canvas. Everything is on Canvas. There's not anything in WebAssign. So let me show you what I have right now on Canvas. There is a module called Start. Oops, not that module. There we go. There is a module called Final Exam module. And we have, or I have, put together basically everything you would need. If you click on this one, it gives you a basic list of all the good stuff, and we'll come back to that. There's final exam practice, and another one I found, practice final exam. So there may well be some overlap in these two, but there must also be some differences, or I wouldn't have put them up. We have a Zoom meeting for this exam, and it's this Zoom meeting here. It's not your class meeting, special one. On your final, I need to see you all, so make sure your camera's working. That's part of the making sure you're not cheating. And here will be where your final is. Right now it's blank. And your final will be in a PDF. You can just look at it and you write all your answers on paper. So it's pretty much like the midterm, right? Same kind of thing. I've got Desmos here, and that will stay here because you might want to sketch things and so on. So Desmos is usable. And here, click on that guy. Here you will upload your working when you're finished. Let me do that. I should be able to do that, student view. So it'll be more what you will see. There you go. And upload, click on that. Wrong one. Yep, upload. Hit start assignment, upload file, choose file. You've already used Microsoft Lens or whatever it is to take a picture, right, of all your working. Hopefully in a single PDF to make my life easy. Let's pretend that's the file, press open, and finally submit. That's it. And you'll tell me when you're finished, and I will go and have a quick look, and I will make sure that everything is there. So let me return to the top one. Good. Do that. Make it a little bit bigger. Our final is cumulative. It's on everything that we've done since start to finish. So question 1 will be from up here. And I can guarantee you that the last question you'll see is an antiderivative. Roughly, because I can't quite remember exactly where it is. I think it was about here was the first 5 weeks, maybe this one as well, maybe here then. The proportion from the first 5 weeks to the last 5 weeks is roughly 40-60. So 40% of your stuff's going to be from the first 5 weeks, and more of it, right, 60% from the second 5 weeks, right? So It's a little bit balanced towards what we've just finished. Things are chronological order. Here is a copy of that Zoom link again. That's me telling you about uploading your work. What you're allowed to use, you're allowed to use your calculator, you're allowed to use Desmos, you're allowed to use any of your notes. So make good notes. And what you're not allowed to do, you're not allowed to use a special types of calculators called algebraic manipulation. And I say, look, if you don't know what that is, it either means your calculator doesn't have it, or you don't need to use it, or you don't know how to use it, so you'll be fine. Can't use the internet, except, go into Canvas. So don't phone a friend, don't go to tutoring, don't go watch a quick video on how to do something, don't do anything like that, right? No help physically with some other person, internet, or just virtually, whatever you want to call it, don't do it. You also can't use any software, which again will almost certainly be online. So don't use Mathematic or whatever. And just to emphasize it, no human contact. Don't phone a friend, don't ask your brother, don't talk to anybody about it. Basically, all those things I think are obvious, but I'll just put them down there. And you won't be able to use WebAssign. It will have disappeared on the day of the final. It'll be fine up till, when do we do it? Wednesday. So it'll be fine up to about the end of Tuesday night, and then it'll disappear on you. Any questions about that? Okay, let's move on and tell you a little bit more detail about the final, and then we'll do questions. The final is going to be in two parts. Section 1 is going to be multiple choice. Like A, B, C, D. And there are going to be 10 questions. They're all worth 5 points. And so that gives you 50 points. In section 1, all I want to see is the answer. No working. If you give me working, I'll just ignore it, because it's right or it's wrong, right? It's A or it's not A, right? So you may have done everything correct, but made the wrong decision. That's unfortunate, but it won't affect you. You won't get partial credit. So essentially, if you want to imagine what that might look like, you might put, this would be your paper, John Smith, and then you would do question 1's an A, question 2's a B, question C is a D, question 3 is a D, question 4, I don't know how you do question 4. D is my lucky letter, so you put in whatever your lucky letter is. So that's all I'll say. Question D is A. There we go. No working, just that. Then we move on to the second section. Oh, by the way, this is chronological order. So your first question is going to be like week 1, and the last question, I guarantee, is going to be on antiderivatives, right? That's the flow. Then you do section 2. Long response. Well, you're going to get 10 questions. On average, 25 points, most of them will be, which gives you 250 points. And the reason I'm saying on average is some questions will be worth 20, some will be worth 30. If it's a big long question or something difficult, you might get 30 points. If it's a smaller question, a lot easier to do, you will get 20, but on average, 25 points. And these I need to see as much working as possible. So even if you would normally skip a line here or, take shortcuts there, especially in homework, which I totally understand, will you resist that for these? Will you kind of show me every step, every reasonable line from start to finish? Because a lot of the points you're going to get when you make a mistake and get the wrong answer is going to come from here, right? Because you'll get partial credit. Can you imagine you did 99% of it, well, 90% of it right, but it should have been +2, not -2, right? Or you wrote a power down wrong, or you made a little mistake here, or you didn't turn it into style points the way it should have been turned into. But virtually everything else was done correctly. If 90% of it is right, you'll get 90% of the points. But I can't do that if I can't see what you did. If all I see is like a line, maybe a bit of working, and then what you thought was the answer, because it was so easy, you did most of it in your head. But God, Murphy's Law, you screwed up and it's not the right answer. I have nothing to work with. So show me as much working as possible. Now, there are things that you can't show me working for. Can you imagine that you might have an equation that's too difficult to solve, right? It's not possible. You just went to Desmos and found out it crossed the x-axis at 1.234. And so you're just going to write down x equals 1.234. Right, I understand you can't show me working in that situation. But anything that can be done should be done, right? So that's what that's about. And so the total comes to 300 points. Since Sunday midnight is the end of all assignments, there are no extensions, I will, midnight Monday, be sending you out your last report. Well, hopefully before midnight, but that's my kind of goal, to send you out your last report. And your last report will actually have an extra bit on it where it will say something along the lines of, you need 120 points to get a 2.0. You need 280 points to get a 4.0, right? I'll tell you what you need to get in the final, because that's all you'll have by that point, right? Everything else will be graded, done, finished. And so that'll give you an idea of what you need to do and what you don't, what isn't going to be possible. Any questions about that? Okay, then let's get started. Has anybody got a topic, a question, something they'd like me to go over? This is your chance.
Can we go over a log or the differentiation question?
Sure. So logarithmic differentiation. And let's see where that is. It's in section 3.6. Well, what logarithmic differentiation process does is it allows you to differentiate really ugly powers or really large multiplications. So it allows you to do things like differentiate the sine of x to the power of cosine x, or x to the power of x, weird powers. It also allows you to differentiate really big, long multiplications. Now, I could do that, but would you agree that would be a really, really ugly product rule with all sorts of other stuff going on? This logarithmic makes that question a lot easier, right? So it's designed for weird powers or weird multiplications or divisions. I could have stuck that in the bottom and it would logarithmic would work fine for that. Okay. Is that the kind of thing you're talking about, Jason, you want to go over?
Yeah.
Okay. Now, we don't have time to do all of them or else there'd be no more questions. From the three that I've got here, which one would you want me to do?
Can we do the cosine x one?
Okay. So, the question's very simple. Differentiate that function. But logarithmic differentiation is not a formula like the product rule. It's a process. So step one in the process is you take the natural log of both sides. That's step one. And this side here will almost always be simplified by using one of the laws of logs, or combination of one of them at least. This is a power. Powers can be written as the power times that guy. So you take the log of both sides, and then the right-hand side, you will use the laws of logs, right? Two things multiplied will become a log of one thing plus the log of the other. Something with a power will become a multiplication times a log. Something that's a thing on the top divided by a thing on the bottom will become the log of the thing on the top, take away the log of the thing on the bottom, right? You'll do that. That's essentially step one. Step two, you now differentiate what you've got here. The left-hand side is always going to be that guy. Because when you differentiate a log, you get 1 over the thing times dy by dx. And this side depends on what you're getting. In this particular question, I'm getting an f times a g. So I'm going to look at that guy and I'm going to say, okay, product rule it is. If you differentiate this guy, you get negative sine x. You then leave the second guy alone. Plus you leave the first guy alone, and then you differentiate this guy. And you're pretty much guaranteed to get the log of somebody in this question. In this case, it's log of sine x. And because of that, you have to be extra careful because it's going to be a chain rule. If you differentiate the log of sine x, you'll get 1 over sine x times the derivative of the inside function, which is cosine x. Are you comfortable with that? So what we now do is basically try and tidy it up. Style points. There probably won't be that much in the way of style points in most questions, but I'll try my best. If I combine these two guys together, what I will get is a fraction with a cosine of x on the top and a sine of x on the bottom. And we know that in trig, very often, fractions can be turned into something else. So what can the fraction cosine x on top divided by sine x on the bottom get me? Cosine over sine. Who are you?
Cotangent.
That's the guy. So I now have cosine x, cotangent x. And essentially what I'm doing here is style points. And there are 3 rules to style points. 1, make it look like the original. 2, factor the heck out of it. And this is this one. If it's a third one, if it's a trig expression, try and use some identity to make it look pretty. You see I'm using a trig identity to get that a little bit nicer. Right, that's step 2 done. Step 3. Once you've differentiated and made it as pretty as possible, the next step is to multiply both sides by y. And this line will always happen. So what you're now going to get is dy by dx is equal to negative sine x times the natural log of sine x plus cosine x times cotangent x multiplied by y. And to finish, what do we do to finish? Well, do I replace this y by, essentially? What does c become? It's in front of you. Just need to know where to look.
Sine x to cosine x.
There you go. And we have now done logarithmic differentiation. Without this process, you could not do that, right? If you looked at that and said, oh, I don't know, maybe it's a weird kind of power rule, right? So I'll just multiply by the power and then take one away. Well, you could do that, but it's not the answer. Agreed, it's not that. And so you need to be aware that the logarithmic differentiation is a niche market, right? It's only there to do certain things, and it excels in weird powers and big long calculations with multiplies and divides and square roots in them. Okay, that was a good question. Where would that appear? Oh, it depends how hard I make it. If I did the one that we've just done here, that I think would be better in section 2 because there's a lot to that. If I gave you x to the power of x, which is a much simpler version of that, I could have put that in the multiple choice, probably would have. Right. So I mean, that question quite naturally could be in either place. Depends how much work's involved, whether it belongs in a section 1 or a section 2. Next question, or topic, or whatever. I'll pick somebody. Yeah, I'll voluntold you. Santiago, picking on you. What bugs you? What do you want to talk about?
Nothing. It's pretty okay.
I don't know if I should be happy with that or sad with that. I hope I'm happy with that, which means that you feel comfortable and there's nothing too much to bug you. The only reason I might feel sad is that why would I think sad? Maybe there's something you don't know. Right? But because you don't know it, you don't know. Okay, anybody want to give me a volunteer? Otherwise, I'll just pick a topic. And since I've not written the final, because I'll be doing it over the weekend, I can do that quite honestly and not feel that I'm giving you a clue or leading you down the wrong pathway. Last chance, I'm picking one now. Okay, I'm just randomly going through this, and here we go. You're gonna have to wait a second while I figure this out. Okay, that'll work. Let's suppose we get one of those questions where it asks us, when is a function increasing, when is it decreasing, and local max and min, and then when is it concave up, when is it concave down, and finally points of inflection. Now I'm going to show you two ways to do this. One is the way you should do it, and then I'll tell you the way you shouldn't do it because it'll get you no points, so you won't do it, right? The correct way to do this, because we have to do it with calculus, is you differentiate this function. Right, so power rule, nothing too straight going on. And then we find the critical numbers by solving when is this derivative 0. So we're going to be looking at when is this guy 0. And if you pull out 3x as a common factor, you get that. And that in turn leads me to x equals 0 as a critical number and x equals 4. So far, so good. Then what you do is you do what's called a table of signs, although it's not actually a table, it's a line. And you put in 0, maybe a -1, -2. Then you go 1, 2, 3, there's 4. And what's that, 1, 2, there we go. You put in a number line, and on that number line, you put 0 and another 0 here, because this number line is going to tell me what the derivative is doing at various points along this range of values of x. And so you have to choose test points. Although these lines don't exist, they kind of help me. Do you see that we're really breaking everything into 3 distinct regions, right? Things that are happening here, things in the middle, things over there. Now, so that gives me a place to go. I will choose -1 as my test point. No particular reason, I'll pick 2, and over here I'll pick 5. And for each one of these test points, we will find the derivative. And I'm not really interested in the number. I am only interested in, is it a positive number or is it negative? So I only write plus or minus here. So it's pretty easy to do, so I'll do it in my head. Negative and negative, that makes this one positive. Positive and negative makes this negative. 3 times that's positive as well. And so we now have that it's positive in this region, it's negative in this region, and it's positive in that region. Now, up to this point, we've pretty much done everything you need to do to identify when the function's increasing, when the function is decreasing, and you will also in a few moments see that we can use this to find where the local max and mins are, right? So in this question here, the original function is increasing. Well, it's increasing when the derivative is positive, because positive derivatives mean the slope's pointing up the way, right? That's what increasing looks like. Negative derivatives mean that the slope is pointing down the way. So it's positive for any value of x up to, but not including x equals 0. And then from x equals 4 to infinity. And then you can also do when the function is decreasing. And the function is decreasing when the derivative is negative. So that's from x equals 0 to x equals 4. Now, at the key points, these guys here, they're called the critical numbers. They will be the candidates for local max and local mins. So let's see if we can get this guy. On this side, it's positive, then it's 0, and then it's down the way. And this one, it's negative, then it's 0, and then it's positive. Can you see a local max at this guy and a local min at this guy? So we can now do that part. There's a local maximum at x equals 0. And the value of that local maximum is whatever f of 0 is, in this case, 1. And there's going to be a local minimum at x equals 4. And the value of that is 64, take away 96, that's negative 32, negative 31, or thereabouts. And we have now done pretty much everything that you should do. So that's the right way to do it. If you make any mistakes, I will be able to see them, right? And I will be able to give you partial credit for all of it. The wrong way to do it would be, oops, a little bit more bending here. The wrong way to do it would be to do that. And you might say, well, it's the right answer. I'm not arguing it's not the right, it is the right answer. I'm not arguing with that. But you did this. And I don't want you to do this. You did it in Desmos. And if you didn't, you should have shown me the work to prove you didn't. So you type in y equals x cubed, take away 6x squared plus 1. Now, if I maybe adjust the windows a little bit, I think I'll do it this way. Let's make this guy negative 44. No, negative 45. That should cover everything. Negative 4. To 5. And what does the y's go to? Negative 31 to 2. Right. There you go. If I shrink it back a little bit, you did that. And then you went and said, oh, okay, it's pretty obvious that that's the local max, 0, 1, right? And there's the local min at 4, negative 31. Oh, it's increasing from here up to x equals 0. It's decreasing from 0 to 4, and it's increasing from 4 to infinity. Do you see all the answers I got are in this Desmos? And calculus 1 is not, I can type something into Desmos and just read the answers, right? That's not what calculus is about. Now, should you do that? Yeah. Shouldn't you do that as a check that you did it right? None wrong with that, right? I already have the answers. I'm going there and saying, do you match what I've got? Because sometimes you put a plus where it should be a minus, right? And you think, oh, that minimum's not there, it's over on the left. Oh, that plus 4 should be a minus 4. You can fix mistakes. Totally okay with that. But not as a replacement. So I'm telling you up front, so you're not going to be surprised. But I gave the right answer. How come you gave me 0? That's not really the important part. It's the proof, the algebra and the calculus is the important part. The answer is just being careful, right? Anybody? Once you've got that, you can do that. Now, if we move on to, here's our original function again. The second part of this process, it is almost an exact copy of what we just did as a process. You differentiate again. You solve when is the second derivative 0. In this case, x equals 2. A much shorter version, thankfully. You do, I know there's 2, there's 1, there's 0, there's negative 1, there's 3, there's 4. And you put a 0 here. because we're now looking at a table of signs for the second derivative. And you do a test point, points. And the ones I'm going to choose would be what, x equals 1 probably. I know 0, I like 0. X equals 0. There's my little dotted line. And over here, I know 3. And I find the second derivative at 0. And I find the second derivative at 3. And here's the second derivative. At 0, the answer is negative. And at 3, the answer is positive. So this guy is negative, and everybody here is positive. I can now do f of x is concave up, and the other ones is when is it concave down. Now it's concave up when the second derivative is positive, right? It's a happy face, positive. And it's concave up from 2 to infinity, and it's concave down from minus infinity to 2. And there's a guy called the point of inflection. And that's the value where the changeover happens. In this case, the point of inflection is at 2, but most of the time they ask you for its coordinates. So its coordinates are 2, 2, 4, 8, 9. 9 take away 24 is negative 15, I believe. And there's your point of inflection. Now, points of inflection only happen when you have a changeover. So if this was negative, 0, and negative, this is not a point of inflection. If it was positive, 0, positive, it is not a point of inflection. It doesn't have a name, it's just nothing very interesting is happening. Now, the same thing is true about local max and min. Couldn't you have pluses, 0, pluses? That can happen. If you wonder what that shape would look like, imagine a shape that's climbing up, levels off, and then decides to just keep climbing. Wouldn't that be a positive, 0, positive combination? So that is not a local max, that is not a local min. In fact, that guy would probably show up down here as a point of inflection. Okay, that was quite a long question, but you know, what can you get in a test? If I gave you the whole start to finish, that would probably be a 30-pointer from section 2, because there's so much in it. I could, for instance, just ask you to tell me when is it increasing and decreasing, which would be that bit, right? I could do that in a multiple choice. I could ask you just to tell me the local max and the local min, right? That would be relatively easy or quick to do. In those situations, of course, if it was multiple choice, couldn't you just go and do Desmos and find it? So I'd probably avoid that question for that reason. Although normally what I do to stop that happening is I make the local max and min happen at weird numbers, like at x equals the square root of 2. Because when you do Desmos, it will just say 1.414. And so I'll know that you've not done it the right way. Okay.
So if it's in multiple choice, we should still not use Desmos.
No, well, you can use it, but I'll probably design it so it won't help. Because I'll say it's root 3, root 7, root 5 over 9, and root 18 over 40/30, right? All of those guys will look very similar to the decimal that Desmos will give you, so you won't know which one it is. I mean, you could use it, but it won't help you if I design it right. Any questions? I get time, I think, for one more. So I'd rather it was something you picked rather than something I picked. Okay, what shall I pick? Off the top of my head. Okay, let's do an optimization question. Let's do a farmer who has a big rectangular field, or he's going to create a rectangular field. He has only got 2,000 meters of fencing, and he wants to break his field into 8 smaller fields, maybe separating his sheep, right? Male sheep, female sheep, baby sheep, old sheep, whatever it is. He wants 8 pens in this big field that's being fenced off. And we want to find what's the largest area that he can do this with, working on only 2,000 meters, right? That's total fencing. So that means the inside fencing counts, the big middle one counts, the whole thing counts. So if you want to solve this question, you have to begin, in this case, by having 2 unknowns. I don't know what this distance is, but I definitely want to find it, and I'm going to call it X. And I don't know what the width is, and I'm going to call it Y. And I have a function that is called the optimization function. In this story, we are trying to find the largest area you could get. And so my optimization function is the area of this. And the area of this is X times Y. And somehow or other, we have got to get X, or Y, I should say, in terms of X. So if you look at this picture here, and I think I should give myself more room, so I'll do it over here. P is going to be the amount of fencing that he uses. It's made up of 1, 2, 3 pieces, X units long, and 1, 2, 3, 4, 5 pieces, Y units long. Are you comfortable about the total amount of fencing is 3 lots of X plus 5 lots of Y? And we know that that's equal to 2,000. So subtract X from both sides, and then divide everybody by 5. Are you comfortable about how I got the Y in terms of X in this story? I used the fact that the total amount of fencing was 2,000, and I converted the total amount of fencing into X's and Y's, and then solve for Y. So we can now return back to the optimization function, the one that we're trying to maximize. And this time it's going to be X times 400 take away 3/5 X. And I'll distribute the X and get 400X take away 3/5 X squared. Now, once you've got your optimization function in terms of X, the next thing you should do is differentiate it. So you differentiate this guy, you get 400, multiply by the power and reduce the power by 1, you get that. And we are interested in essentially when is the derivative 0, right? The critical numbers. So I will subtract 400 from both sides. I will then multiply both sides by 5 because I'm too lazy to do it in one go. I will then divide everybody by 6. And the answer, by -6 I should say, the answer is whatever that guy is. Let's find out what that guy is. 2,000 divided by 3, make it a fraction. And the answer is, that can't be right. There we go. It's that. And to finish the question then, let's assume that they asked us not what x is equal to, but what would the length and width be? If they did that, your answer would be that the length is equal to x. So that's 1,000 over 3 meters. And that the width, which is y, which is this guy, and so that becomes 400 take away 3/5 of 1,000 over 3, cancel, 200. Oh, at least that's a nice number. It's 200. So you would say that the length was that guy, and the width was that guy. And if the question had said, what is the maximum area, you would have done that calculation. And there we're finished. Now, do you see how these are really slightly ugly? I mean, it's not hugely ugly, but you see how that's a 3, for instance? If I was trying to make this to stop you using Desmos instead of calculus, well, for starters, if I don't see this working, it's not happening. But let's say you try and bluff me, I will make it 7ths or something. Right, and do you know what 1,000 over 7 looks like? It looks like nothing. Now, when you go to Desmos, it won't tell you that. Won't Desmos probably give you 142 point, was that an 857? It won't be, that's what you will see. Well, if I see you writing down out of the nowhere 142.857, I know you didn't do any calculus. I know that you just went into Desmos and found out, you know, where the top of the hill was and the bottom of the hill, and you didn't do anything that was even remotely calculus. Now, if this class had been use Desmos to do stuff class, I'd be pushing Desmos and saying, don't worry about this calculus stuff, just plug it in and get the answer off the picture.